To really understand what is special about quantum bits and why they can provide such a large computational power, we need to look at what happens when we take more than one qubit. Let's take the example of a spin, which we know how to visualize. The superposition of the 0 and 1 state of a single spin is simply the spin pointing to the right. So that doesn't seem so strange. But now let's take two spins and make them interact with each other. This can happen, for example, because each spin produces a tiny magnetic field in its vicinity, and this field changes the energy of the other spin. Remember that we can rotate a spin by applying an oscillating magnetic field at the frequency proportional to the energy difference between the 1 and the 0 state. But if there is another spin in the vicinity, the total energy depends also on the state of that spin. Let's say I prepare both spins in the 0 state, and then I put spin A in the superposition of 0 and 1. Now I try to flip spin B by applying the frequency it would respond to if spin A is in the 0 state. But actually, since A is in both the 0 and the 1 state, then spin B both flips and doesn't flip. The resulting state is a superposition of 0-1 and 1-0. The 0-1 branch of the superposition is created because spin B flips to 1 when spin A is 0. And the 1-0 branch is created because spin B remains 0 when A is in the state 1. This kind of superposition is perfectly legitimate, but it's really special. In this state, I have absolutely no idea of where the two spins are pointing, but I do know that they point in opposite directions. This is called an entangled state. If I separate the two spins after I have prepared the entangled state, and I measure, for example, spin A, and I find it in the 0 state, then instantly spin B acquires the 1 state, no matter how far apart it is when the measurement takes place. This is what Einstein called dismissively the spooky action at a distance, but now we know from many experimental tests that this is the way quantum mechanics really works. In the context of quantum computing, entangled states represent a strikingly non-classical computer code. There is no way you can write in your desktop computer a code where two bits have no value but have the opposite value. But you can do so in a quantum computer. And the more qubits you have, the more these entangled quantum computer codes proliferate and grow exponentially with the number of qubits. Gaining access to these entangled quantum states is the key to exploiting the exponentially large computational power of quantum systems. At the same time, entangled states are very fragile and can easily be destroyed by unwanted interference from the outside world. This is why building a quantum computer requires so much effort and investment. We need to create a perfectly controlled environment where large entangled states can be produced and manipulated without interference.